Welcome to Computer Architecture, COM 2125. Today we'll be discussing direct mapping in cache memory. Now, direct mapping, or DMs, are the one thing every male should know how to dive into. So that's what I'm here to teach you kids. Now, direct mapping is divided into two parts. The bits giving the location of the word on a line in cache, and the bits identifying a block in main memory. Sort of like if you want to know where a girl's phone number is, you gotta get her area code first, and then you gotta get the actual number so that you can send her messages. No, direct mapping is probably the simplest form of cache and the easiest. Much like the DMs, a phone and a WhatsApp message is much easier than homing pigeons. Trust me. Now, to check for a match, it's simple because the tag shows the line we need. Now, after that, direct mapping is also inexpensive. However, thrashing may occur. Thrashing occurs when a program, follow me. A program in main memory which uses two blocks of main memory try to identify both address the same line in cache, and the data inside keeps repeating itself over and over and beating itself violently because he can't remember her name. Now, we need to address. Now, before we do that, what in the name of computer science is cache? With a computer, cache needs to be addressed first when we look for things. Anything really, you need cache. Women, cache. Computers. No, if you don't have cache, where do you go? To your mom, your main memory. No, with your main memory, things address a lot slower because we know that when we want things from our mothers, we have to wait. But if you have cache, there's no wait process. So, why is there no wait process involved? Simple. Imagine if we were looking for one rice grain in this whole bag of rice, as opposed to maybe, I don't know, on this guy's spoon. Eat. Good. Now, a computer knows the rice that we actually frequently visit. So when it actually looks for rice for our stomachs, it'll check cache, our spoon first, and then it'll go back to the whole bag of Indian girl rice. It's that simple. So how does this help us with address structure? We'll see now. Now, we're ready to move on to address structure. Address structure is broken into tag S minus R, which tells us which line in cache we're looking for. R, the line of cache, so that we know where to put it back once we're done with it. And W, the word, which is pretty much what we came for. And when we sum these all up, that is our total address. Now let's do the math. W is the number of bits to uniquely identify a location on a line of cache. But depending on how the question is structured, they'll pretty much have to give us this number for line size. So 2 to the W will equal our line size. 2 to the W equals 16, therefore 2 to the 4 is equal to 16. And what it means our W is 4 bits. If you check back our example, 4 bits is the size of our word. Next, R is the number of bits to uniquely identify a line of cache. 2 to the R is the number of lines in cache. And to find that out, we'll take the cache capacity and divide it by the line size. The cache capacity will be given to us in the question most likely as well. For this one, the cache size is 1 megabyte. 1 megabyte is the same thing as 1024 kilobytes. It will be much easier for our calculations if we just convert it. So we take 1024 kilobytes, divide it by the 16, which was our line size above, and it'll give us 64K. 64K is 64 times 1,000. But not really 1,000 because we're in binary. 2 to the 6 is our 64, 2 to the 10 is our K. So together it's 2 to the 16 and R equals 16 bits. S plus W now is the number of bits to uniquely identify each main memory address. S plus W is the entire address of our word. But 2 to the S plus W is 16 megabytes, which is the memory size, which would probably be given to you if you had to do a question. Same process as before, 2 to the 4 is 16, 2 to the 20 is your M, so that means that 16 megabytes is 2 to the 24, and that 24 is our S plus W. But we're not done here yet. We came here to look for our tag, our S minus R. So we'll combine our previous answers. We'll take the S plus W, 24, and we'll take R, which was 16, and W, which was 4. 24 minus 16 plus 4 gives us 4 bits, and that's our tag. Daria, give them a question.
As you can see on the screen right now, you're given a simple direct mapping question. The equations which were used throughout the video are given at the side. You may pause the video now if you wish to complete this question yourself. If not, the answers will be provided in just a few moments. To answer this question, we start by writing out the important information from the question given. Writing out the block size, main memory, and cache capacity makes answering this question a lot easier. Using the equations given and using the method shown earlier in the video, we can easily see how each answer was calculated, and we can show the representation on the right hand side of the screen. For part B, our first step is to convert our hexadecimal number into a binary number. After which, we realize that our binary number has 28 numbers, whereas our addressing length was 27. This is an easy fix, as we can just ignore the most insignificant bit, which would be the 0 at the front there. After which, we separate our binary number into groups of 11, 13, and 3, our tag, line, and word numbers that we calculated earlier. After we have these separations, then we can just separate back out into our hexadecimal format and convert the numbers back into hexadecimal. And then we have our answer. Thank you.